This is question 2 of the practice midterm 2. This is a question about MDPs. Consider the MDP drawn below. The state space consists of all squares in a grid-walled water park. There is a single water slide that is composed of 2 ladder squares and 2 slider squares, marked with vertical bars and squiggly lines respectively. So we have the ladder squares here, and then the slide squares over here. An agent in this water park can move from any square to any neighboring square unless the current square is a slide, in which case it must move forward 1 square along the slide. So that's over here and over here. The actions are denoted by arrows between squares on the map and all deterministically move the agent in a given direction. Okay, so on the map we have arrows indicating the actions. So for example here, in this state here, there's an action available to move there, an action available to move there, the one moving up here gives a reward of 0, down here a reward of 0. The agent cannot stand still, it must move on each time step. Rewards are also shown below. The agent feels great pleasure as it slides down the water slide, +2, steps over here and over here. A certain amount of discomfort as it climbs the rungs of the ladder, that's -1 here and a -1 here, and receives rewards of 0 otherwise. The time horizon is infinite. This MDP goes on forever. The first question we're asked, how many deterministic policies are possible for this MDP? So in general, the number of deterministic policies is given by product or I equals 1 through n, where n is the number of states, of the number of actions available in state Si, which in this case, let's look at how many states we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 states. Out of these 14 states, there are 3 we don't have 1 action available to us. We only have 1 action available here and also here. So 3 of these states we have 1 action available, so that's 1 to the 3. And then in the other 11 states we have 2 actions available, so that's 2 to the 11. So we have 2 to the 11 different policies for this MDP. Let's look at the next question. We're supposed to fill in the blank cells of this table with the values that are correct for the corresponding function, discount, and state. First one here, V3 star S, with gamma equals 1.0. And here our state is equal to A. So we start with A, which is the state over here. And we're asked, what is the optimal expected value? And everything's deterministic. So the optimal value we can accumulate starting in state A, acting for 3 time steps. Well, the best we can do starting in state A, acting for 3 time steps is to, well, in 3 time steps we did not reach the +2 reward of the glide. So the best we can do is 0 at all times. Starting from state E, which is over here, well, there we can glide twice, which gives us a reward of 2 and 2 for a total of 4, and then next we'll have 0 rewards. Then for 10 time steps left, starting in state A, well, the optimal thing we can do is to move around 10 steps. We'll get twice a -1 for a ladder, and then twice a +2 for a glide, for a total of +2. Which is over here. here, acting for 10 time steps, the best we can do is just glide and then retain rewards of 0 after that, so that's 4. And here now we have a discount of 0.1. Now let's see, what's the best we can do starting with state? Well, one extreme case is again to follow this path here. In this case, we would step at time step 1, we would get 0. Time step 2, we would get 0. Time step 3, minus 1. Time step 4, minus 1. Time step 5, 2. Time step 6, 2. And then all zeros afterwards. And counting this would be 0 plus 0 plus 0.1 squared times minus 1 plus 0.1 third times minus 1 plus 0.1 4 times 2 plus 0.1 to the 6 times 2. This total is less than 0, so with this type of counting, it's actually better to stick around in the 0. And the optimal value we can get starting from state A, 0. Starting from state E, the best we can do is to glide down twice, which will give us 2 and 0.2, for a total of 2.2, and after that we'll get all zeros. For one time step left, left over in A, up here, either way we would get 0. Actually, this time left not available, so no worries. In E, moving left gives us a reward of 0, and with only one time step total, that's all we're going to get. 0. First moving left. So, for A, we can't move left, so nothing to be considered here. For E, if we first move left, if we first move left, then we'll get a reward of 0 moving left, and the next thing to do would be to move right minus 1, and then plus 2, and then 0 afterwards. So we would end up with 3 E star long with a discount factor of 1. What we get starting from E. Well, if we could act infinitely long, we could go around the loop infinitely many times, and going around the loop gives us plus 2 total. So if we do times, we'll have plus 2 for E. If we go around the loop infinitely many times, every time we go around plus 2. What if we get to act infinitely long, but the discount factor 0.1? Well, we've seen in the computation here earlier that with a discount factor of 0.1, you actually don't want to climb the ladder to then go down and glide, because of the discounting, the cost you incur climbing the ladder is higher than what you get back from gliding later, because the gliding later is so heavily discounted. So what happens with the discount factor is that for you just get 0. You wouldn't want to climb that ladder to then glide. And starting from E, you wouldn't do the glides, giving you 2.2, and after that you never climb that ladder again because it's not worth it.